Section 8.4, we just did the exponential function, and now we want to do trigonometric functions. It all comes down to sine and cosine, so we're really just going to do sine and cosine. Again, we have the question of what are we going to take as the definition of these functions. Well, we're going to basically define them by differential equations. And we're going to show that there exist solutions to those differential equations, which we will call sine and cosine. And then, as we'll see, we'll prove a couple identities related to them. We're never going to prove, there's some things that we're not going to prove today, but, you're definitely capable of going and looking at the proofs. Things like the sine and cosine give you the unit circle, this kind of stuff. Okay, so let me just state our first theorem. 8.4.1. There exist functions. Remember, when we did this for the exponential, we called it capital E, just because until we knew it was the exponential, we didn't want to call it that. So here we're going to do capital C and capital S. Okay, so there exists two functions, capital C and capital S. So that we want the second derivative of C to be what?
Negative C.
Negative C. And the same with sine. Okay. Note, just by writing the second derivative, we're sort of implicitly saying that these two functions are twice differentiable. So not only do they each have a derivative at all points, but they each have a second derivative at all points. Okay? And the second thing is that we need to specify the initial conditions. So C of 0 is 1. And these are second order differential equations. So if you remember back to diffie-q, we need two initial conditions. C prime at 0 is 0. S of 0 is 0, and S prime at 0 is 1. Okay. We're not going to put uniqueness in this theorem. That's going to be a later theorem. We're just going to prove existence right now. Okay. Everybody clear on what we're trying to do? Now, obviously, if this kind of theorem showed up in differential equations class, you would just say, well, yeah, sine and cosine do this. We're pretending we don't know that sine and cosine exists, so we're going to develop them. Okay, so we're pretending that all we know is what we know about differentiation and integration and polynomials. And we're trying to get sine and cosine out of that. Okay, so we're going to define two sequences just like we did with E. We're going to do it inductively again, just like we did with E. And here are rules. C1 is just the constant function 1. S1 is the function x. Okay, now we need to define Sn for n at least 2. We're going to define this to be the indefinite integral of Cn and actually this works, the Sn definition works for S1 as well, so we wouldn't even have to write that. And then we want to define Cn plus 1. Okay. If you think about it, it's not, if you think about what goes here, we actually want 1 minus the indefinite integral of the sine. Okay, and we want this to hold for all natural numbers n and all real numbers x. Okay, are there any questions?
Yeah, why did you cross out the S sub 1? Oh, gotcha.
Yeah. We don't need to say that because that the general definition for Sn gives us that. So we just integrate 1 from 0 to x, and we get x. Any other questions? Oh, okay, so we're following the same. We're following the same outline as we did for E. There's really not any surprises here. What did we do for E? We said we had a similar kind of thing. I mean, I guess it's a little bit more complicated this time because we're going back and forth between C and S. But by induction, each function Cn and Sn is a polynomial. So it is continuous and integrable. Okay, so let's just say, C1 is clearly a polynomial, so it's continuous and integrable. Therefore, S1, which I've crossed out the line where we define it as x, we're just using the line where we define it as an integral. Well, since C1 is a polynomial, it's integrable, and its integral is continuous. And actually, its integral is a polynomial. So we see that S1 is a polynomial. And then we plug that in, and we see that C2 is a polynomial. And then we go back, we see that S2 is a polynomial, etc. They're all polynomials, so they're all continuous, so they're all integrable. So therefore, Cn and Sn are well-defined, continuous, and I guess I'd want to say and integrable for all n. I mean, I guess I already, I said above that they're continuous and integrable, so we might as well just say that they're well-defined.
Dr. Goddard?
Yeah.
So, when we say continuous and integrable, you're saying that it's continuous on all of the reals. And when we talk about the integrability, are we talking about on all of the reals or on all integrals?
Integrability holds for all the reals. Oh, I'm sorry. Yeah.
Because we had something similar in the exponential function proof. We had only all real line.
So you'd like me to add that?
Yeah, I just wanted to make sure that was.
Yeah.
I guess you can integrate, right? Because I guess you get 0, tricky, weird stuff.
Yeah, so you're certainly correct to point out that I need to add every bounded interval, because you can't be integrable over the whole real line unless you're the 0 function. Yeah, I mean, we just haven't defined what it would mean to be integrable over the whole real line. Okay, so good. They're integrable over any bounded interval. Okay, now, following exactly the same outline as e to the x, by the fundamental theorem of calculus, S and C are defined in terms of integrals, so we can differentiate. And what are we going to get? You take the derivative of Sn, and you'll get Cn. And you take the derivative of Cn plus 1, and you'll get, well, what will you get? Okay. So we get the derivatives we expect to get. Okay. Now, we can use, just again like we did for e to the x, we can use our inductive definition here to actually compute these. And we know there's a nice pattern we should see. It's the Taylor polynomials, although we haven't talked about Taylor polynomials in this class, so we're not going to call them Taylor polynomials. They just actually come out of repeating this inductive definition. So by induction, we have now, I'm not going to give the inductive proof, but I hope it's clear that there is an inductive proof. that would be our Cn plus 1, and our Sn plus 1 would be its integral. So it would be x. Okay. Now, first of all, I hope you recognize these formulas. But at least for me, this is a different direction to approach them from. So when I do Calc 2, I compute these as Taylor polynomials. So these are, the coefficients are the derivatives. And I'm using Taylor's formula. The way we got them here is we got them by integration, repeated integration. Okay, so it's almost the opposite direction as we do in Calc 2 when we're doing Taylor series. Okay, and again, I didn't do the induction here, but I hope you can just stare at them and see that that's going to work. So what should we see? We should see that Sn plus 1 is the integral of Cn plus 1. And you can just check term by term. That checks out. And we're not appealing to any kind of term by term integration theorem here because it's a finite polynomial. Okay, it's just a polynomial, so we integrate it term by term. That's how we do it. Okay, and then we'd want to check Cn plus 1. Well, Cn plus 1 should be 1 minus the integral of Sn. Well, you get the 1 minus, and then you imagine integrating Sn. That with, and you see the signs, because of the minus, the signs are going to flip. Okay? So, by induction, we're going to get those formulas. Okay, so now that we got the formulas, we can prove some uniform convergence. Remember, we can only do uniform convergence on a bounded interval. So let's consider a bounded interval. So all we're going to need now are those formulas. Now, let's look at x in that closed bounded interval and see what we get when we compare the tails two terms in the tail, so Cm and Cn. Okay. With e to the x, I did this in the forward direction where I actually said the conditions on m and n up front. This time, let's try and do it in the backwards direction where we derive the conditions on m and n. Okay. So now, what would be the difference between Cm and Cn? Well, I guess we should say which one is bigger. Let's say that m is bigger. Okay. And now you just have to figure out how we're going to do this. The first term that is not subtracted here is going to be minus 1 to the n, x to the 2n over 2n factorial. Okay. Because that's not a term of Cn. Cn would stop at x to the 2n minus 2. Okay, because our definition above was Cn plus 1. Okay. Then we get some more terms. And now what would be the last term in this difference? It would be the last term of Cm. And Cm, its last term is minus 1 to the 2m minus 2. X to the 2m minus 2 over 2m minus 2 factorial. Okay. Now, it's inequality time. Let's pull out some x's.
Professor?
Yeah.
Exponent to 2m minus.
Sorry, Olivia, you were breaking up there.
How does the exponent for the negative 1 get to 2m minus 2?
Maybe the easiest way to think about it is that if we were looking at Cm plus 1, we would go up to 2m. And cosine only has the even powers. Okay, so since we're looking at Cm instead of Cm plus 1, we're not going to have that last term, and so we're going to have to stop at not 2m, but 2m minus 2. That's the term before 2m. I hope that makes sense.
I guess I'm confused.
Yeah, I thought it would be like, I thought the X meant,
It's m and not m.
yeah.
M is the bigger one here.
I was thinking why instead of 2m minus 1.
Are you... I heard an m minus 1 is... That's what's in there.
I understand the fact or the exponent of x. I
Oh,
don't
okay.
like the exponent for the negative 1 should be half of what the exponent for x is. That's why I'm confused.
Oh, I'm
That's what I
sorry.
was trying to say.
I'm sorry. Yeah, you're right. You're right.
Yeah. Like, wouldn't it be,
There you are. Thank you.
so it is m minus 1. Gotcha.
Okay.
Yeah, that makes more sense.
Of course, it doesn't matter at all because we're about to crush all those negatives. Okay. Now, it's inequality time. We want to get rid of those x's. Let's pull out an x to the 2n. But we're going to replace it with the largest that x could be. Well, okay. Let me write it out this way. Okay, we're going to pull out an x to the 2n. But actually that comes with an absolute value, but the absolute value will move in to take the absolute value of x. And now we're going to be left with some stuff in here. Fine, I'll write some of it. You know what? Now would be a good time. Let's get rid of the signs on the inside. Right? We're doing a less than or equal to. If we make all the terms on the inside the same sign, that can only make the inside bigger. And this will give us a little bit less writing. Okay, then what's left over? 1 plus x squared over 2n plus 2, 2n plus 1, and then plus, and then we've got an x to the 2 times m minus n minus 1 over some product. Okay. Now, absolute value of x is less than or equal to a. Okay, now we want to bound each of these guys. Okay. Each of these terms, each of these fractions has the same number of terms on the top as it has on the bottom. So I'm saying you get the same power of x on the top as you have terms that are multiplied on the bottom. The terms that are on the bottom, they're all at least 2n. In fact, they're all greater than 2n. So we make the fractions bigger if we change them all into 2n's. Okay. So in my bound, I'm going to change the top to an a and the bottom to a 2n. Okay. And then you realize that actually it would be a little bit nicer to think about this as a geometric series in a over 2n all squared. By which I mean, this last term, it would be a little bit nicer if we thought about that as a over 2n all squared raised to the m minus n minus 1 power. Okay, now same as with e, we can get an upper bound just by letting that sum go off forever. So now notice that in here we have a geometric series in a over 2n squared. Okay. So now we say, well, if we want this to be small, what do we want? And we're allowed to make n as big as we want. Okay, we just want eventual convergence. So n is allowed to be huge. So let's say that if n is at least, what do you want to put here?
I think we want to make this geometric series be 1/2 to the n. That would give us a nice.
1/2 to the n is a good one. Although it's hard to get this thing to be 1/2, right? Right, so this is our common ratio, is this guy. It's going to be hard to get that to be a half without involving some radicals. And so we'll always choose pretty over a good bound. Let's make this equal to 1/4. So if we want a over 2n to be a half, then let's see. N would be 2a? No, n would be
just A, right?
yeah. Okay. And actually, okay, so I solved that. That's not really what we want in our argument. What we really want is, we want to say if n is greater than a, then a over 2n squared is less than 1/2 squared equals 1/4. Okay, so now so now we say we wanted n to be at least, to be greater than a. Let's go add that. Up to our proof. We have m greater than n before. Now let's have m greater than n greater than a. Okay, and then we have times, what's the sum of the geometric series with ratio 1/4? It's 1 over 1 minus 1/4.
4/3.
Yeah, 4/3 a to the 2n over 2n factorial. Okay. For a fixed a, and that's what we're thinking about, we've got a fixed a that we're dealing with. This is going to go to 0. Okay, now again, this is just like we did with E on Friday. This Cauchy condition on the tails gives us our uniform convergence.
So just to clarify again, this is saying, so we've shown as long as we pick an n sufficiently larger than a, we can make the difference in the tails small enough.
Mm-hmm. Small enough for any x.
For any x.
Well, for any x in that interval, in that closed interval we're looking at.
Okay.
Mm-hmm. And our conclusion is that therefore the sequence Cn converges uniformly on minus A to A.
I have a quick question about this limit to zero.
Mm-hmm.
And goes to infinity.
Yeah. I think for our the office Wi-Fi is rewarding us for our last lecture, and you cut out again. So you questioned about that limit, but I didn't get your question. Is it just
So
how do
are
we
we
compute
saying
it?
here that n is going to infinity? That's why we're making this go to zero?
Oh, good point. Yes. Yep.
So we say for m greater than n greater than a, but we're taking this limit as n goes to infinity?
For m, so yeah, that's a really good point. But so what's going on is for n greater than a, well, m greater than n greater than a, we have this inequality. Okay, we can't say we have that inequality for smaller values of m and n. But as long as m and n are large enough, we have that inequality. Now, all we cared about in the end was the limit as n goes to infinity. Okay? So that's why we don't care that the limit doesn't hold for all m and n. We just care that it holds when they get big enough.
I see.
I hope it makes sense.
So we're also saying that as m goes to infinity, even though that's not in this inequality anymore.
Yeah, m, right. M's going to have to go to infinity because it's greater than n.
Okay,
Yep.
thanks.
Okay. So we get uniform convergence on this bounded interval. Uniform convergence, of course, implies pointwise convergence. So we can define C of x to be the limit of Cn of x. For all values x. Okay, now we don't care that x is in the interval, because what we're saying is for any x that you want to define C of x at, just take your interval to be big enough that it contains x, and then you have uniform convergence, define it to be your limit there. Okay, now what carries over? All of the Cn's were continuous, so C of x is continuous. I'll just write C of x is continuous. Okay, that follows from our observation that all the C's are continuous, and our theorem that if you have uniform convergence, then continuity carries over to your limit function. Okay. And of course, we also know what's C of 0. It's got to be 1, because all of the Cn's were 1 at the origin as well. So their limit is just going to be a limit of the constant 1 sequence. Okay, now what about sine? Let's not... Okay, so for sine we could totally just repeat this argument. We could do all these inequalities all over again. But let's try not to do it twice. Let's try to use the relationship between sine and cosine to get it for free. Okay, so as long as we have our conditions, okay. I want to add a condition on x. Okay. The SM and SN. The S's are had to go find it here. The S's are the integrals of the C's. So, go back down here. The absolute value of Sm minus Sn would be the integral from 0 to x of Cm minus Cn. And I've got an absolute value sign out front. Oh, and I just committed a classic stupid calculus error. I have my x both in and outside of the integral. Okay, we need to integrate with respect to t, just so it's a different variable. Okay. Well, now we can use our bound. What is our bound? The difference between Cm and Cn is at most 4/3 a to the 2n over 2n factorial. Okay. Now, you see we're integrating a constant from 0 to x. And x is at most a, or the absolute value of x is at most a. So the absolute value of this integral is at most what we get when we put in one more a. The whole point of this was to get the uniform convergence of the S's from that of the C's, and we just did. Okay. So this also converges uniformly on every closed and bounded interval, or really just every bounded interval. And now again we define a limit function. Okay, and just like always, we define our limit function to be the pointwise limit. We get that S is continuous. Again, that's just the SNs are continuous, and we've got uniform convergence, so it carries over. And if we look at 0, we will get 0 because all of the SNs are 0 there. Okay. We haven't done anything about differentiability. And remember, our theorem says we have to get the right second derivatives. Okay, all we've done is we've got functions c and s. So let me see if I can sketch this. Here's the thing. Since Cn prime is equal to minus Sn minus 1, let's go back and see where that came from. Where did that come from? Just right there with n instead of n plus 1. We take the derivative of Cn, we get minus Sn minus 1. Okay, let's go back to where we were. Okay, those minus Sn minus 1s are converging uniformly. So we can say, and don't worry, I'm aware of the time. I think we can finish this real quick. The derivatives of the C's converge uniformly. Well, and we should say on this interval. Okay, so we can I guess I might just need to sketch the rest of this. So we can define C prime as a limit and we had this relationship between the primes and the derivatives. So this actually carries over. Okay, and from this you can get that the second derivatives are what you want. Okay, so that's not the end of the proof. I guess I will have to refer to the book for the rest of the proof. Okay. Let me also say that in the book, you should look at corollary 8.4.3. That shows you that the Pythagorean identity, which remember just says c squared plus s squared equals 1 for all values of x, that follows really trivially using derivatives and integrals. So basically from our perspective, that's really trivial. Again, the book proves uniqueness of C and S, but that proof uses Taylor polynomials, so that's a topic for next semester. And the other one I will draw your attention to is theorem 8.4.8. This gives estimates for sine and cosine. These are the estimates we've talked about before. These have come up a few times in class, stuff like that. That s of x is bounded by minus x and x for positive x. Okay, so sorry for running a few minutes over. That is section 8.4 for you. Let me stop